Welcome everyone and to one of our remaining meetings following the end of the academic semester. We just heard an excellent ITC colloquium by Neil Mandelker, and he will tell us some more about his work on valence disk instability in high redshift galaxies. And after that, we'll hear from Michael Weber from LMU. Where is Michael? He's over there. He will tell us about the interactions between photoevaporative disk winds and embedded giant planets. And after that, we hear from Ronen Tamari. Ronen, over there. From Astera Institute, who will tell us about Sensemaking Networks, making visible the dark matter of scientific research. Okay, that should be interesting. And finally, Rachel McClure from the University of Wisconsin-Madison, who will tell us about classical bulge impact on bar resonance evolution. Go ahead, Neil.
Thank you, Avi, and thanks for giving me the opportunity to speak here. So I wanted to talk about something that was completely disconnected from my ITC colloquium just now, which is why I'm going to talk about this. This work on violent disk instability, together with a graduate student at Omri Ginsberg and Avishai Deckel, Philippe Bourneau from CEA, Dan Severino, Mark Krumholtz, and Joel Premack. This is work that kind of has been like resurrected. This is related to things that we worked on several years ago, as you'll see in the slides. But this year we had one paper out already, and Omri is currently finalizing the second paper. So this has kind of been revived, and it's a good chance to discuss it with you all. So the context is clumpy disk galaxies at high redshift during cosmic noon. Observationally, so these are observations and these are simulations. They're not meant to be the same systems. It's just a happy coincidence. But about 60% of star-forming galaxies at redshifts 2 to 3 are observed to host so-called giant star-forming clumps. As you can kind of see here, there are these very bright knots in the UV. Clumps have typical masses of about 10 to the 8 solar masses. The combined star formation rate in all the clumps in a given galaxy works out to be about 20 or so % of the total star formation rate in the galaxy itself. So these are pretty important for the overall star formation history of the universe. These are, of course, also seen in cosmological simulations by a wide number of people using a wide number of codes and a wide number of different groups. I would say we all perhaps disagree about the evolution of these clumps after they've formed, but we all agree that they form. And that's really what I'm going to be discussing. And I want to talk about the clump evolution, which could be a whole other talk, and here there's a lot less agreement. But about the fact that they form, we all agree. So let's talk about how they form. So the classical understanding is that these clumps are formed as a result of tumor instability, when the tumor Q parameter, which is basically the stabilizing effects of velocity, dispersion, and rotation, divided by the destabilizing effect of gravity. When the tumor Q parameter becomes less than 1, which happens very commonly in high redshift disk galaxies due to high gas fractions and high gas densities, driving up the gas surface density sigma. Q becomes less than 1, disks become unstable, you form giant clumps, and everything seems to work out. But if you think about it for more than a few minutes, you should really be bothered by the fact that we're relying so heavily on tumor theory to explain these high redshift violently unstable disks, because tumor theory is meant to be applied in the linear regime for axisymmetric systems. These disks are far from linear and far from axisymmetric. So it could just be a happy coincidence that it all works out. But when we look in the cosmological simulations, this is a paper from 2016. I said this was a few years old. This is the Vela cosmological simulation suite, and we took great care to actually measure tumor Q in these systems using a fancy 2-component Q, separating gas and stars separately when we estimate tumor Q. And you can see that throughout most of the galaxy, Q is between 1 to 2, between 2 to 5, and even between 5 to 10. Q is only less than 1 inside the dense clumps that are already formed. So that's odd, but you might say, okay, fine, that's not all that surprising. I don't care that Q is, very large in some random patch of the ISM. Maybe where clumps are about to form, Q is as small as it should be, and then I can hold on to the theory, and all would be well and good. I should actually note, sorry, the fact that Q is so small in collapsed clumps is pretty meaningless. Of course Q is small in a collapsed clump, because a clump is a highly nonlinear object with a very high surface density. So of course you're going to drive Q less than 1, but that says nothing about the conditions leading to the formation of clumps. Now, as I said, okay, to be fair, this doesn't say anything about the conditions leading to the formation of clumps either. It's a random patch of the interstellar medium, but in the same simulations, we can identify clumps and track them back through time until right before they collapse in the first place, in the protoclump-like patch, and ask, okay, what is Q in the protoclump patch just before the clump formed? And you still get that Q is very often between 1 to 3, sometimes even greater than 3. So that's really weird. That shouldn't happen. And just to show you what that looks like, this is surface density of gas and stars, and this is our two-component Q. And I've highlighted here a patch that's about to collapse into a clump. You can see here that Q is above 3. I take it forward in time. Clump has begun to collapse. Q is now beginning to go down because the surface mass density is going up. But again, that doesn't mean anything. Of course Q goes down once the surface mass density goes up. It doesn't mean anything. Q is very small here. Okay, great. But so what might be going wrong here? Well, as you recall, the tumor Q parameter in the numerator has that velocity dispersion. Let's talk a few minutes about velocity dispersion, in particular how that might be divided into compressive versus solenoidal motions. So this is like a random velocity field and a random patch. Within this patch, you can take the mean velocity field in the patch. You can have a linear correction to that velocity field and some nonlinear residual. The linear correction to that velocity field can be divided into 3 well-defined components. One representing compression and expansion about the point, which has 0 curl and the same divergence as the initial field. A second representing solid body rotation around that point, which has 0 divergence and the same curl as the initial field. And a third which represents shear around that point, which has both 0 divergence as well as 0 curl. Now these two components are colloquially referred to as the solenoidal component of the velocity field, whereas this is going to be the compressive component of the velocity field. Now in equipartition, if I have a truly random velocity field in equipartition, you expect the solenoidal component to have twice as much power as the compressive component. You can kind of hand-wavily understand that because solenoidal motions are in 2 dimensions, compressive motions are just in 1 dimension. So if everything is in equipartition, this has twice the power as this. And that's kind of what you implicitly, under the hood, expect sigma to behave like in tumor Q. But if for some reason, locally, you could have enhanced compressive motions and dehanced solenoidal motions, you could have a very high sigma, but that doesn't necessarily promote gravitational stability. It could actually promote gravitational collapse if you just happen to have collapsing motions. And this idea was first made popular in 2014, a paper by Florent Renaud et al. This is a merger simulation of the antennae galaxy. And what they see is that right around the time of the first pericentric passage, the ratio of compressive modes to solenoidal modes, which started out in equipartition when the galaxies were in isolation, that flipped. When that flipped, that led to an enhancement of gas undergoing fully compressive tidal forces, as opposed to both compressive and expansive tidal forces. These tidal forces were fully compressive. No, I apologize. The other way around. The compressive tidal forces were caused by the merger. That caused the compressive to solenoidal mode ratio to flip, and that led to a burst in star formation. So compressive tidal forces as a result of a major merger led to enhanced compressive turbulence, led to enhanced star formation rate. Could that be what's happening in our simulations? No. When you globally decompose the velocity field in our simulations, this is from our paper from earlier this year. I don't have my name on it, that's a shame. This is our paper from earlier this year, 2024. When you globally decompose the velocity field in those same simulations that we looked at the high tumor Q, you see, depending on if you like volume weighted or like mass weighted, there's a slight 10% difference, but overall, you have roughly 2/3 of the energy in solenoidal modes, roughly 1/3 of the energy in compressive modes, as you would expect. That's not surprising. These simulations are not undergoing major mergers, so the know-it-all model shouldn't really apply. But this is globally. What about locally? So this is that same collapsing protoclump that I showed you before that was undergoing collapse with a high Q. So this is that same surface mass density, but now here I'm showing you the ratio of the power in compressive modes versus total turbulent modes, but not just compressive, specifically compressive modes with a negative divergence. So this is not expected to be 1/3 in equipartition. This should only be about 1/6 in equipartition. But you can see that in the protoclump region that's about to collapse, this is really large, right? Like 70% compared to 16% that you would expect in equipartition. And as the clump begins to collapse, at this point, it goes up, enhanced by the collapse itself. Now, once the clump is formed, this actually drops way down. This drops way down mostly because in these simulations, collapsed clumps are actually rapidly rotating around their axis. So therefore, internally, you've enhanced the solenoidal component. In addition to that, your starburst has ejected material in supernova winds, so that's still compressive, but has a positive divergence rather than a negative divergence. So it's also not counted here. One more moment. And this is specifically looking at now the histogram of what you get in the protoclumps versus random patches of the disk. So in the protoclumps, you have a strong preference toward large compressive modes in the protoclump regions, whereas in the random components of the disk, you're at roughly equipartition. Now, the really cool thing is if you do the same exact experiment in a non-cosmological isolated disk galaxy simulation, you do not see this. You get that in the protoclumps themselves, as well as the random patches of the disk, you're in roughly equipartition, and clumps only form due to tumor instability as you would expect. So this feature, which is robust in cosmological simulations, must be externally driven. So high Z, massive disk galaxies are violently unstable. Massive clumps form in regions that should be linearly stable with Q greater than 3. In cosmological simulations, clump formation is associated with large compressive flows. This is not seen in isolated disk simulations where tumor theory seems to hold, which implies an external driver with a compressive turbulence. What might be driving this? It could be streams, as we talked about in the ITC colloquium. This is that same galaxy on larger scales. These are inflowing streams which hit the disk right where that compressive modes led to clump formation. So this could be intense accretion by cold streams driving turbulence in the disks. It could be local tidal fields induced by perturbations, clumps, and spiral arms, etc. Preliminary work led by Omri Ginsberg, a student, suggests that both of these are indeed at play. And you could also have feedback-induced shocks. And it'd be fun to think about alternatives to tumor Q for instability analysis, which actually take all this into account. That's it. Thank you.
Here, there is data on clumps like that in high-redshift galaxies. And can you elaborate how close your expectations are to what is seen and whether there are any discrepancies?
So I'm not aware of studies that have tried to take the velocity field in high-redshift clumps and decompose them into compressive or solenoidal modes. I do know there are ways to do that observationally, and one idea I would really love to do, I even started to do this a little while ago, but the project never saw it come to fruition. Yeah, so it's certainly possible. This hasn't been done yet, but it's certainly possible to do, and it's something I would like to do, is to try and decompose the observed velocity field, at least the line of sight velocity, which is what you can access into the compressive and solenoidal component, and try and measure this. The disadvantages and what makes this hard is that, again, the clumps that you observe are already collapsed objects. So that's not really going to be indicative of what's happening in the protoclump patch regions. Reinhard Genzel does measure very low Q values in the clumps. But again, that doesn't mean anything because the clumps are already collapsed. So of course their Q is very low. So it's not clear how to do this correctly, but I think it should be. We should talk about this. It should be done.
Comments, please.
This is great. Did you think about the ways how to show that decision turbulence, the turbulent compression? Because in principle, one can make exactly the same counter argument as you did against tumor, right? So if the clump is collapsing, then there will be compression modes simply because of that. So
Yeah, no, that's exactly right, and that's why I think this, without this plot, I don't think it would be a convincing story. But this plot, to me, is what sells the story. The fact that we don't see this in isolated galaxy simulations, right? When you look in protoclump regions of isolated galaxy simulations, everything seems to be in equipartition. We only see this in the cosmological simulations. That to me implies that there is some external driver of turbulence which is, predominantly compressive. Whether that's inflowing streams or tidal perturbations, that's the second paper, but something is happening.
Do you try like gas-rich galaxies?
Yeah, so I didn't really go into the definition of the simulations, but these are isolated disk simulations using the Ramsey's code meant to mimic a redshift 2 gas-rich galaxy with an initial gas fraction of either 40 or 50%, and typical sizes and masses that you expect from high redshift galaxies.
Right.
Maybe a quick comment before we move on. You could be looking for present-day analogs, right? I mean, the largest star forming region in the local group, 30 Doradus, is exactly located where the tidal feature connects with the SMC. And that could be either a tidal effect or it could be one of these crashing things, probably more likely a tidal effect. But there is a correlation between where these massive star-forming regions in the Milky Way or in the neighboring galaxies sit and external perturbations. And I think there you have much better access to the global velocity field than you have in Genzel's one-point things. So maybe that is something to look at.
That'd be very interesting, yeah. Also worth looking at would be stuff from the Dynamo survey, which is, it's not as local obviously as that, but it's certainly at low redshift, and they're supposed to be analogs of these clumpy star-forming galaxies, very rapidly accreting. But yeah, we should maybe talk more about that this afternoon.
Let's thank Nir again.
Okay, so you can hear me? Hello everyone, my name is Michael Weber. I'm a postdoc at LMU Munich, working on the evolution of protoplanetary disks, and especially with special focus on disk winds, more precisely photoevaporative disk winds, and I will explain in a second what this means. But in general, we are interested in disk winds because we know that they are most likely one of the key components or key mechanisms responsible for the quick dispersal of protoplanetary disks. So after a couple million years, most of the protoplanetary disks are gone. So this, of course, sets the upper limit for the time planets have available to form. And we also know that planets can create strong substructures in their disks, especially giant planets. They can carve gaps around their orbit. They can create spirals. And with two such important effects on the evolution of protoplanetary disks, the idea of this project was to see whether or not they interact with each other. So maybe let me start by quickly explaining to you what photoevaporation is. Okay, this doesn't work. So imagine you have a star, and this star is surrounded by a protoplanetary disk. It irradiates the disk with high energy irradiation, UV, X-ray, and this heats up the surface of the disk to high temperatures, which creates a strong pressure gradient, which is able to drive away an outflow, a photoevaporative wind. Now you can also have magnetic winds. Oops, sorry. Oh, this does work. I won't speak about magnetic winds today, but they are very important as well. Now imagine you have this wind that is constantly carrying away material from the disk, and we also know that most disks or most stars accrete material from the disk, so there's a mass flux from the outer to the inner disk. And at some point, the mass flux will be balanced out by the mass loss in the wind, and at that point, a gap will open in the disk. The inner disk will drain onto the star, and once this is drained, it will leave the outer disk completely exposed to the irradiation so that it can quickly photoevaporate away on a timescale of a few 100,000 years. So this is the typical picture we have of disk dispersal by photoevaporation, and of course there's been lots of work going on in this field. And one of the models is the EUV and X-ray photoevaporation model by Giovanni Picogna. This is what we use in this project. So most of these simulations are two-dimensional radiation hydrosimulations. But to include these effects in other models, in planet formation models, in population synthesis models, you need a bit, something with a bit less computational demands. So it is often useful to derive a one-dimensional radial mass loss profile from those simulations. You can apply these then in your model. This is also what is used in this work. So this is work by Giovanni Rosotti, who simulated a giant planet in a disk at 20 AU. So the radius here is on the vertical axis. You can see at 20 AU, there's a deep gap. You can also see spirals. And in the top panels here, this is the case where this photoevaporative mass loss was included using such a one-dimensional radial mass loss profile. And you'll see that if you include photoevaporation, you get rid of this inner disk very quickly. And the reason is mostly because the planet blocks a significant portion of the mass flux across the gap from the outer to the inner disk, which gives photoevaporation an easier time to remove the inner disk. And of course, with the inner disk being gone much earlier, the outer disk will be exposed to the irradiation much earlier. And that way, the planet effectively reduces the lifetime of the entire disk. So this is also often called planet-induced photoevaporation, or PIPE in short. And this work, as well as all the other works so far that looked at the interaction of planets with photoevaporative winds, made use of such a one-dimensional radial mass loss profile. And of course, these profiles are derived from simple 2D models without planets, without substructures, so they don't account for any additional effects that might arise from those. And this finally leads me to the actual motivation of the project. So we wanted to have a full 3D model with a planet in it, with its substructures and the wind, and see how do they interact with each other. Are there any new effects? So there's a lot going on here. This is basically the setup. We have a disk around a 0.7 solar mass star. We have a Jupiter-like planet in there. This is here. This opens up a gap. And these white lines are all streamlines in the wind. But I would like to draw your attention onto these green tubes. Those are streamlines traced back from within the planet's Hill sphere. So you can understand them as example paths that the gas could take towards the planet before being accreted by the planet. And you'll see that some of them lead through the wind and fall directly onto the planet. Some go into the gap and then later on are accreted by the planet. So there's a new paths available through the wind by this. And I would like to go into a bit more detail here. So what you see here is a cut through the disk. This is the azimuthally average density. The contours are these dashed lines that give you an idea of where the gap is. The planet is at 5.2 AU. And in white here, the velocity field of the wind. So you can see that from within the gap, we do not have a wind. We don't have the required pressure gradient there, mostly because the inner disk is shadowing that region. On the contrary, since we do not launch a wind here, we lack the pressure for this, the pressure gradient for the surrounding wind to be supported from in this region. And what will happen is that the wind will be driven away from radially interior of the gap and exterior to the gap towards the region where it falls down into the gap and in that way delivers material into it. And this is actually quite efficient, which I would like to show to you with a short animation. So this is now two cases. On the top without photoevaporation, on the bottom with photoevaporation. And I have put a tracer fluid in the surface layers of the inner disk. On the right here is the midplane, which is currently empty. But now if I start to play this, you will see that very quickly photoevaporation can transport this tracer through the wind into the gap, from where it can then also viscously be transported further. And this is much more efficient than what you see in the purely viscous case on the top. So as a result, we have a much higher density in the gap. So this shows you the surface density, and the green line is the case with photoevaporation, and the solid black line here is without, and there's a more than an order of magnitude difference there. which is one of the key takeaways I would like you to remember. Photoevaporation can partially refill that gap. And of course, with more material available in the gap for the planet to accrete, the planet will accrete more. So at least in our very rudimentary way of implementing accretion in this model, we find a factor 2 increase in its accretion rate, which means that the planet would grow about twice as fast, which is another key takeaway. Another very important effect is that we have an increase in the mass transport across the gap. So what you see here is radial bins, and each bin indicates how much mass that originates in this bin can be transported across the gap. The gap is shown as this gray shaded region. So if it crosses the gap from the outer to the inner disk or the other way around, it will show up in this bin. And you'll see that the green line again is much higher everywhere. And we can also start transporting material from the innermost disk to the outer disk, which isn't possible without the wind. In total, we find 5 times higher mass transport rates across the gap in both directions. This can even exceed the viscous transport rate. And the way this works is that when the wind refills or brings material into the gap, we still have the planet in the gap, which is trying to keep the gap open. So it pushes that new gas aside, either to the inner edge of the gap or to the outer, and that way it can cross the gap. And this in combination with the fact that we actually also lose less material in the wind because some of it is coming back into the gap. We have about a 2.5 times lower mass loss rate in the inner disk. This means that we have more material available in the inner disk in general. So also the inner disk will live for longer. And now, if you remember, this pipe effect, when the inner disk is completely gone, we will quickly photoevaporate the disk away. But now that the inner disk lives longer, it means the entire disk will live longer, which is completely the opposite of what we would have expected from this pipe effect going into this. So we find about a 3 times longer lifetime in this particular model compared to the case without a planet. So in summary, the key takeaways I would like you to remember is that photoevaporation can redistribute the gas via this infall mechanism into the gap. This leads to higher accretion rates onto the planet, to higher mass crossing rates, and to longer lifetimes for the inner disk and the entire disk. And there's many more effects, so if you are interested, please come talk to me or have a look at the papers. Thank you very much.
So Michael, do you see any time-dependent effects? Because obviously the filling takes some time and the planet has an orbital time. And do you see like waves being excited as a result of that? Or are the times too different? You don't get that.
So we can't run this for long-time scales. We don't simulate this over longer times. But as far as we have simulated it, it's fairly steady state.
And the dust is not playing a big role?
We don't include
You don't
dust.
have dust. Go ahead.
I'm about related to that. How much dust do you expect to see in trade with the gas that's flowing into
This depends very much on how much dust we can get up to the disk surface, and if we can get it up there via, I don't know, instabilities or whatnot, then you have you can only entrain the small grains, so up to about 10 microns. So I don't expect this to play a huge role for the dust, but it all depends on how efficient you get the dust up to the surface.
Please.
Thank you. This is fascinating. Thank you for sharing. So how can you connect these results to something observational, be it disks or planet properties or demographics? Is there a particular observation you're trying to explain?
That's a very good question. So I was trying to do different things actually. First of all, I was wondering if we could maybe see that this infall in typical wind diagnostics. And actually try to predict synthetic emission lines of the trace winds, but unfortunately it doesn't trace that region very well. It's not traced there. What is actually possible is that you get variations in these line profiles from the spirals that the planet creates. And these are also present in the wind in a sense. But I also experimented a bit with CO kinematics, maybe if we could see it there. I haven't been successful there yet, so I think it's a bit difficult to observe this. And then maybe if you think on this chemistry and isotopic fractions, maybe you could in some way connect this to observed meteoritic records, using the idea that you have a different composition in the inner disk than in the outer disk. So that was just a thought I had, but I would like to discuss this more, but I don't know exactly how we would go.
Well, sometimes theory is done without any motivation to test it against the observation. It's just a matter of an important process that should be included. Yes?
On that line, since the disks are so much more long-lived and you have that material and the accretion rates are different, would you expect a different distribution of planet masses when taking this into consideration? And could you compare that to the observations that we see?
Yes, yeah. I think it would be very nice to include this in populations increases, but you would need to describe this with different parameters, and the parameter study, which I haven't done.
The issue is that there are so many parameters that it would be difficult to single out just this one for that context. Any other questions, comments? If not, let's thank Michael again.
Is this working? Do you hear me? Cool. Let me just extend my screen. Cool, yeah, hi everyone. So yeah, my name is Ronen Tamari. This is not about astrophysics, so it's kind of a different talk. I actually don't even know what the context is. I'm coming in here after meeting Avi and Juliana, and they were interested in the ideas of like alternate modes of publishing in science. So it's more a talk about like meta science as opposed to science. It's about changing the ways we think about how we share research and communicate about science. The Astera Institute is basically, it's a Berkeley-based startup accelerator, but it's a kind of different startup accelerator that's focused on open science, like accelerating science and improving the ways for sharing and publishing science. And I'm part of that program. Our startup is called Sensemaking Networks, and yeah, I added dark matter so that it would at least have some connection to astrophysics. And yeah, thanks Avi and Juliana for inviting me here. Who uses social media for their research here in the group, just so I get a sense? Wow, not so many people. Okay. Who is using? To promote research, you mean? To promote, to find research, to talk about research. Oh. Who isn't using social media? Okay. 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 Yeah. Well, maybe. So I don't know. Maybe this talk won't be interesting to you at all, but we'll see. Hopefully. I come from AI. I did my PhD in AI. We use social media all the time. So maybe I'm just biased by my field. Who can resonate? Does this resonate with anyone? Okay, good. So at least we have some connection. So yeah, this is real. I mean, we all researchers feel this. It's kind of information overload. Yeah, the sense that you have way too much on your bookshelf and not enough time to make sense of it all. And our project is really rooted in that insight. Access to information doesn't translate into the capacity to make sense of information. We have open access science, we have preprints, and that fills up our bookshelves, but it doesn't really help us answer the questions of what to read, who to follow, what's the novel ideas that I should be paying attention to. So that's kind of at the individual level, but at the macro level, it's also a problem. It kind of translates into stagnation of scientific progress. And there's research on this. There's one interesting theory that I've especially focused on in my research, which is a theory called dark knowledge, or knowledge in the dark. And they talk about this kind of exponential increase in the rate that we're publishing data and information, but the knowledge kind of remains stagnant. I don't know, is this something you feel in astrophysics that's happening, or is this not a problem in astrophysics? Okay, there's kind of a sense that maybe, yeah, in AI this is definitely a problem. So there's kind of an untapped potential knowledge that results in the failure of translating raw information into knowledge. And these are kind of vague terms, and if we have a little time, I can also go into a little more detail on them. But sense making kind of comes in here, because it's really the process of translating information into knowledge. It's from the cognitive science literature, and that's basically in a nutshell what it means. And people also call it research synthesis. So they also say in this paper that advances in research synthesis are critical for tackling dark knowledge. And that's kind of what is going to help us harness more of this kind of untapped dark knowledge. And the question is really, how can we improve research synthesis and sense making? And in my work, what we've been focusing on is the potential of social media for doing that, science social media. It's kind of unrecognized and untapped, but very important part of the research synthesis process. That's our claim anyway. So yeah, this is the reason I also called it here dark matter of scientific research, because we have kind of the visible scientific record, the papers, the citation networks that we're all familiar with. But papers are surrounded by this kind of dark matter of science social media, which is actually where a lot of the research synthesis is happening. People are interpreting results, they're debating things, they're discussing new findings, and it exerts real influence on science. In AI at least, if you get tweeted by the top influencers in AI, you're going to get a lot more citations actually. And this affects people. People look at your Twitter follower account for when they're doing job interviews. So it's become a real thing, but it isn't actually even recognized as science. So it's kind of this paradox. It's not recognized as science, and even if you wanted to kind of make it recognized, it'd really be a hard challenge because it's scattered across podcasts, videos, posts, closed platforms like LinkedIn, ResearchGate, all these different places. So it's a really challenging data problem as well. There's an interesting kind of partial solution to this. I don't know, have any of you heard of nanopublishing? Okay, yeah, because we talked about it last time. Okay, so most people have not heard about this. This is interesting. So there's a trend in science of kind of making more and more fine-grained the scale at which we share information. I don't know if maybe that happens in astrophysics too. Instead of just papers, now we share code, we share maybe data. Nanopublication is kind of the extreme end of this. Nanopublication is kind of like a scientific container for a tweet. So it's basically, this is an example of nanopublication. Like me saying I read a paper could be a nanopublication. People find that kind of amusing or crazy, but hopefully I can convince you that it actually makes sense in some way. I did not invent this. This is a real nanopublication template. This is not my project either. This is an existing project that I'm kind of building upon. And the interesting thing about nanopublications is that it's on the scientific record. They're a recognized solution. It's developed by some academic institutions over in Netherlands. They're machine readable, which is interesting in a way that social media posts are not. You can tell here that everything is structured, so it's like a kind of like fields you're filling out. So it's very structured. Everything is easy to aggregate at scale. It's kind of like a knowledge graph, if any of you are familiar with those. So it's a really good way to share information in ways that are, if you're sharing a lot of large scale and high complexity information. But on the flip side, they're hard to publish. No one really has time to go and fill out these forms and choose the right template. And there's also a lack of incentives for even creating them in the first place because no one knows about it. So it's a new project, and yeah, so that's another challenge. But what we're noticing is there's actually really interesting kind of complementary relation with social networks. Social networks are exactly the opposite of nanopublications. They're not on the scientific record. They're not machine readable. But they're very easy to use. And there's strong incentives to using them, as we saw earlier. And if you follow any researcher on social media, the ones that are active at least, you'll see that they're sharing a bunch of, they're nanopublications, basically. They're talking about recommendations for research, critique, reviews, saying they've read something. So they're already, a lot of us are already nanopublishing, but just don't know it yet. And what we're doing, so this project, the Sensemaking Networks project, and this is our app called SenseNets, it's AI-based nanopublishing and discovery tools for researchers. And the idea is to start building this kind of, moving from this kind of messy, chaotic social media to a more organized kind of semantic web of science and helping connect some of the things that are happening on social media and making them more part of the scientific process more intentionally. And I can show you, I can show you, so there's one I can just show you a nanopublication. So this is actually, I'm showing you two versions of our app. This is a version of our app that it looks at my social media feed, and it's just trying to help me create nanopublications easily. So it's recognizing the references that I'm sharing, and it's trying to, we're using AI to create the keywords and these semantic relations. What is my relation to the reference? Am I critiquing it? Am I reviewing something? Am I endorsing something? We have actually automatic publication, so I can do it manually, but I can also publish things automatically using rules. This is the nanopublication version of my tweet. Are any of you familiar with RDF, the language? Semantic web, okay, yeah, so, okay. This is different in AI field. Cool, so this is a nanopublication, but the thing about this is on the record now. Elon Musk can't decide that someone has to pay money to see this tweet now, or it's safe. So this is one part of sort of making the data available and open to researchers as well as other people that just want to browse this kind of information. And the second thing we're building is a kind of feed. So this is more on the not on the publishing side, but on the experience of actually seeing what other researchers are doing. So here is a feed that aggregates these nanopublications from other researchers, and we use these because we have these semantics, we can add more you don't have this on Twitter that you can kind of choose special subcategories. So here I'm looking at opportunities. Maybe I'm interested in funding opportunities, or I'm interested in events or grants or that kind of stuff. Maybe I'm interested in people recommending research or podcasts. And we can do further kind of sorting of this based on people's preferences. And yeah, one of the main things we're doing here is we're also aggregating from different social networks. So we have Mastodon, Blue Sky, and Twitter in one place. And we're also filtering out non-research related stuff, or at least we're trying to with AI. It's somewhat subjective in some cases, but yeah, you can click on these keywords. You can go and see other people that are talking about topics you're interested in. It's a kind of interesting experience. A lot of these new, I don't know if people use Blue Sky or Mastodon. It's a kind of messy feed, and it's hard to get the interesting parts of it. So having a kind of filter, just show me the research, has been really valuable for us. It's still under development. We hope to release the first version in a few weeks. And yeah, that's, I guess, about it. Yeah, happy to answer any questions. And you can scan the QR code if you want to get updates on the project, get in the loop.
Thank you, Ronen. We have done one experiment in astrophysics, and that was 32 years ago. The archive, a place where people post preprints, was established. And I remember the first 25 years went fantastically well. You could post whatever you want. And then for some reason, there were so many posts, there were some crackpots posting, and so they developed, the administrators developed a moderation system, and actually blocks some very good papers right now, because we don't know exactly what tools they're using in AI to select papers to block or at least delay. But obviously they don't work perfectly. They work maybe 95% of the time, and 5% people suffer from it. People submitting very legitimate papers are being delayed. And so the question is, doing this with these nano publications, how do you avoid the noise or a lot of crap from people who just express opinions because they hate someone. You know, like that happens on social media.
Yeah. Yeah, that's a great question. I mean, I think the interesting thing about nano-publications, and if people are familiar with Blue Sky, the new social network, they're also adopting a kind of decentralized moderation principle where instead of having one like central authority that's doing the moderation, it's more decentralized. And then, yeah, there's specialized sort of algorithms, and it's more like a marketplace of moderation. And then, yeah, so these are, I think, new ways we can use. You can get better results by distributing the effort.
Yeah, I think the main criticism of social media has to do with the moderation system. I mean, there were claims that it was politicized, especially in the case of Facebook, and so that's really the Achilles heel.
Well, this is exactly why things like nano-publications are so powerful. This aspect of machine readability that I mentioned. So just by adding these tags and using some AI to do some initial filtering, you get already a much cleaner experience for your feed. And then if we also have people sort of helping curate for each other, you're marking things that you think are valuable or not valuable, then it's quite easy. And community notes is another example. There are mechanisms you can use to, do this kind of, use crowd intelligence to solve some of these issues. So the combination of structured data, AI, and some of the collective intelligence, I think, would give a good experience.
You have your trust in democracy that the majority is actually very sensitive. Any other comments, please?
So I feel like you're taking a very textual approach here. I can imagine a paired approach that's much more sociological. Like, if I run Sebastian in the hallway, he says, "Oh, I read this great paper, you should see it." I don't feel like there is any desire to turn that into a nano publication, but that is scientific information and knowledge propagating through a social network. So I guess are you working with anyone who sort of has experience thinking that way and thinking how to sort of pair these two approaches to the idea of kind of how we're turning data into knowledge?
So do you mean that we're looking at kind of social media posts, but not at other ways people are sharing this kind of same information, but in other channels, sort of?
Well, I guess you can apply a whole theoretical framework about, I'm sure there are people who spend all their time thinking about how I know you can treat cultural constructs in a sort of epidemiological model of why do some things propagate and some things don't. Just seems like there's that sort of whole way of thinking about these concepts, which is a very different tradition, but it seems like it might have something to offer.
Not sure I still understand. You mean?
Do you hang out with sociologists?
No. Just maybe one point about the different modalities for sharing. So we're focused here on text, people sharing stuff online. I think there's other work on identifying mentions of research in podcasts or in seminar presentations. So ideally, we collect that kind of thing. People are looking at conferences as a way to also collect some of this. So the idea I think is not to create a nano publication of every time someone mentions research, but it is to better connect, meaningful kind of mentions of research. So if someone is doing a really great explainer video on TikTok about research, that's worth a nano publication to connect them. We don't want to surveil people. It's more a tool for helping us make sense together of the literature.
Any other comments, questions? Yes? Go ahead, over there. Yeah?
I want to ask about peer review. Have you thought about this sort of decentralized network and nano peer review or peer review on Twitter or?
Yeah, that's a great question. And it's interesting when the word because it has publication in the word, so people feel like it might be peer reviewed. There's no thought of the project does not have any concept of peer review. So it's just you can create without any kind of limitation. But I think with things like Avi asked and tools like community notes, for example, and these kind of community notes is a kind of peer review, micro peer review, some posts. So I think these kind of things, using upvotes, downvotes, different kinds of signals, would work well with this framework.
Okay, last question. Go ahead.
It seems like social media amplifies extreme views. Is there any way to damp that?
Yeah, so this is another reason why we don't want to be, if a scientific community, this is happening again in AI, because so many AI researchers use Twitter, it's kind of beholden to the algorithm that Twitter uses, and that algorithm, like you said, amplifies kind of extreme things, polarizing content. And that's not what you would want for the scientific communities. But when we're starting to use more open networks, and Blue Sky is also a good example, then yeah, you don't need to, you can choose different algorithms. So a lot of it is a question of who controls the data and who controls the algorithms.
That's the key. History
A
is,
lot of cost.
well, history is obviously depending on who writes it. Okay, let's thank Ronen again.
We'll try that. Okay, hi. I'm McClure. It's a pleasure to be here. Thank you for inviting me. I'm going to be talking about the classical bulge impact on bar resonance evolution. I highlight here the archive number up on the upper kind of, right echelon on this slide. This paper has been accepted. I'm about to get it back in with the slight revisions. Please go have a look, because I only have 10 minutes here. And I'm here for another day if you want to talk. I'm here tomorrow, too. So some of this work was completed with Gus Bean, so I will highlight that. But what we're going to talk about briefly is just galactic structure. So I want to highlight the kinds of galactic structure I'm really focused on, specifically thinking about bulges, bars, and BPXs. So bars being elongated central features, bulges including both classical bulges and pseudobulges, so things that have kind of inherited rotation and things that are more remnants of hierarchical assembly and are random motion dominated. And then a specific class of pseudobulge, which is often talked about separately from pseudobulges in general, is going to be our boxy peanut X feature down here in the bottom right. We do have a BPX in the Milky Way. I'm going to highlight that up top. So this is mid-IR imagery, stellar counts, I think, of stars directly in the Milky Way. And then below that, I'm showing a couple other examples of X's. And then I'm going to highlight that 45% of local barred galaxies do have a BPX, massive local barred galaxies, including the Milky Way. So these are common features. And so understanding how stellar bars and BPX pseudobulges evolve with different initial central bulges is something that is of interest. But really kind of the question that I tackle in this paper is maybe more along the lines of, does the presence of a BPX always mean the same thing for a galaxy's history? And spoiler alert, no, it doesn't always mean the same thing, but also sometimes yes, in an important way. And so that's what we're going to talk about. So the models that I'm using in this work are a set of 4 in-body simulations. These were run by Gus here. So this is, I want to highlight that over here. On the right, we're seeing them evolve in time. I have 0% bulge, 4%, 8%, 16% of the disk mass. And what you'll see is that the inclusion of that central bulge does change how, over time, these features evolve. But I will jump forward, because I'll play this again for a second here. I want to highlight that all 4 of them do end up with really nice, very pronounced boxy peanut X features. So these are fixed in the bar frame, as I'll play this video again now, from the time where they all have reached the strong bar threshold. And so purple in all the plots will always be our 0% bulge, blue, orange, and then green increasing in bulge mass compared to the disk mass. I'm going to draw your attention to the purple as it undergoes that buckling event there. So that is the kind of classical way that we think of bars evolving into BPXs from the early time of this work, where the bar becomes disrupted vertically. It undergoes an asymmetry event that's temporary, and then you are left behind with the BPX. But what you'll notice is that you never saw that kind of event down here in our 16% bulge simulation. So on the right side of here, I'm showing over time since the strong bar threshold is reached. So we kind of align these simulations because the larger bulge does delay bar formation. And so on the bottom plot, we're looking at the actual amplitude of the BPX, so a measure of how much stuff is above and below the disk at any time. And in the top, we're measuring the bar amplitude itself, colored here by pattern speed, but then in the bottom, and for the rest of the plots, colored by a measure of the asymmetry. So asking how asymmetric above and below the disk in the bar region is the galaxy, is this model at any time. So darker colors being more asymmetric, so like here. You can see there's darker there, there's darker here, but that we never really have any darker times in the green. So the two things I want to point out before we think more about kind of the question I posed of like, does the presence of a BPX always mean the same thing, is that we end up with a stronger final bar amplitude with increasing bulge fraction. So I'll highlight that in the top plot up here. The bar amplitude over time is ranking at the very end of the simulation with highest bar amplitude corresponding to highest classical included initial bulge. And then going down from there. So you can see green, orange, blue, purple. The other thing I'll highlight, though, is, as I pointed out in the purple simulation, where there is no central bulge to kind of steady the process of the BPX formation, there's a very sharp increase in the BPX amplitude that corresponds with that sudden emergence of this kind of asymmetry event, right, this bar buckling. And so we also have an event like that in purple that's not, or in blue, in the 4% bulge simulation that is not as pronounced, but has a very similar sudden growth event of the BPX. But we do not have that in our with increasing bulge fraction. So with increasing bulge fraction, we get a stronger final bar, but we also get no sudden BPX growth events. And so the question here is, what's happening? What is this telling us? If we look at a BPX at the end, we see that a galaxy has a BPX. What can we learn about a galaxy's history from that? Given that we now see that there are different things happening in the intermediary time. So to measure this, what I did is I characterized the orbits throughout the simulation. So these are large in-body simulations. I actually took the orbits, using them in the time evolving potential. And what I do is I characterize their directional frequencies to find resonant populations, to select on resonance populations. So I start here with the bar supporting orbits, just so you can see that we do have this kind of steady increase in all 4 simulations. Spare this little guy here who has no central bulge, so fun things happen in that simulation. But we do have a steady increase overall in all the rest of the simulations of the fraction of orbits that have bar supporting 2 to 1, so 2 radial maxima per 1 azimuthal period characteristics in their directional frequency components. If I then instead think about the fact that I'm looking for something that's making a vertical extension of the bar to form a boxy peanut X feature, what I'm going to look for is a vertical 2 to 1 population. And so at the top here, I'm showing you the fraction of the things that have equal horizontal and vertical frequencies. So if you had a bar-like star that has horizontal 2 to 1, and then you also happen to have it so that the radial frequency is equal to the vertical frequency, you then have equal radial and vertical frequencies, and that's what I'm counting in the top plot. And what you see is you have a spike that corresponds to, this vertical line is marking it in all the other plots, but you have a spike that's corresponding to the time where you have the maximum fraction of things with equal radial and vertical frequencies. And you see that you have that spike in purple, we have it in blue, and then we also actually have a somewhat different spike in orange, more steady, more drawn out. But what we're seeing there is that there's an increase in the fraction of stars that have equal horizontal and radial frequencies. And those correspond to an increase in the fraction of stars that have both horizontal 2 to 1, bar-like frequencies, and the vertically extended frequencies that I call XV 2 to 1, because they have either the vertical 2 to 1 analog, so 2 maxima in the vertical direction per 1 azimuthal period, or they have the frequency such that they've kind of crossed that threshold, but they are still vertically extended. So they have longer periods in the vertical direction compared to a 2 to 1 ratio. And so what we see is that this very well traces this Bresel population of the having horizontal 2 to 1 and having the XV 2 to 1 frequency ratios very well traces the growth of the BPX, and also that the increases that happen here happen at the same time as the fraction of stars that have equal radial and vertical frequencies kind of has a spike. And that we never see that spike in green. And so here, I'll replace that top plot with the BPX amplitude, so you can see that these very well trace the growth of the BPX. What we're seeing when you actually watch the simulation evolve in real time is well characterized by calculating what fraction of stars happen to have bar-like and vertically extended orbits. So we're able to select very well on those. The question is, what actually studies this process? And what I found in this work, which is kind of the main result of the paper, is kind of demonstrated in this lower plot. So looking at, once again, just the fraction of stars that have equal radial and vertical frequencies at the top. Down here, what I'm actually showing you is the fraction of stars that have not accounting for bar-like frequencies at all, not including that in this fraction, but just the overall distribution of stars, how many of them are vertically extended. And so when you add a central bulge at the beginning, you increase the fraction of stars that are already more vertically extended compared to your disk without the bulge at all. And so basically, if 50% of the stellar population is at XV 2:1, then you stop having a sudden increase or a much higher fraction than you would have normally of stars with vertical and radial frequencies that are equal. So essentially what I find here is that until you have 50% of the stellar population with these vertically extended XV 2:1 orbits, you will have your bar stars crossing this vertical 2:1 resonance as well, and then you'll get an overdensity, kind of an unusual spike in the fraction of stars that are undergoing resonance crossing. And what stops that process is when you hit the 50% threshold. And so with that, I didn't start my timer on my thing, so I have no idea how much time I have left. Sick. This is my summary slide. So coming back to, does this always mean the same thing if you have a BPX? The answer is yes and no. So no, you can have a dramatic resonance crossing event, but all BPX growth is always due to bar-like stars crossing that vertical 2:1 threshold. So that's why I say sort of yes. You don't have to have any kind of underlying gravitational instability like a buckling event that's driven by like a fire hose instability, but instead you just have to have bar-like stars that are crossing your vertical resonance in order to get a BPX. And when that happens a lot, because you don't have 50% of the threshold already vertically extended, you can get a dramatic event. So there you go.
Rachel, you refer to stars. There is also dark matter. Does it?
Yep.
Well, I guess the dark matter is shaped by the bar, but that also affects the bar potentially.
Yes.
Is it playing a significant role?
Yeah, so we do, it's a live dark matter halo. We do get a shadow bar as expected. When you look at the actual, literally how your dark matter evolves in these simulations, it does kind of mimic and interact with dynamically the structures that form in your disk of stars. So that's how you slow the bar in the first place, typically, right? So your dark matter is actually torquing on the bar, and that's part of how you slow down your bar over time. So dark matter absolutely plays a role in this. I haven't looked into the resonance structures in the dark matter, though. But there are other people who have done some of that, like Lee with vinegar, I think, maybe.
Thank you. Comments, questions? Yes, go ahead, Tom.
So what makes the peanut thinner in the middle?
Right. So let me see if I can jump to the morphology. The inclusion of the bulge really does have kind of somewhat of an impact on whether or not your BPX will be thicker in the middle or kind of thinner in the middle. So I go to this because it shows that boxy versus X-shaped kind of division. There's recent work that's shown that this is more of a time-dependent thing. So I'm, of course, going to blank on the name of whose work that was, but it's sometime in the last year. They did some work showing with the simulation that their boxy peanut X feature does evolve from being more boxy to more X-shaped or one or the other. So one of these seems like might just be a later time progression than the other. This is part of the reason I don't make a division between the two of them. In my simulations, I think that you can see that the inclusion of a central bulge makes it so that the central part of your bar and your boxy peanut are actually at least partially taken from the bulge itself. So they fill that central space in a way. So having the central bulge does affect how the center of the BPX looks in my simulations, but that's not to say that it's also still not kind of a time division between these two stages of being X-ier or boxier. Does that kind of answer the question?
Since there are no more questions, I just wanted to point out this is the last meeting of the fall semester. The weather will get better hopefully in the spring. So have a wonderful break, winter break, and happy holidays to everyone.
Thank you.